Okay. We have an exam next week, a week from today and a week from tomorrow. Exam 4, I guess. And it looks like where we are with the material, this usually, most semesters, this seems to, one exam falls this way. Like we just haven't gotten enough, we won't have gotten enough done of the next stuff early enough to have conservation of energy and linear momentum. So there's only one topic on this, and that's circular motion. Yes. Yeah, there's always, so the final is cumulative, but it also has the last topics on it. So there'll be
any more
quizzes on all of the remaining exams, yeah.
So there will be lecture quizzes
Yes.
on the exam.
Yes.
Just not part of the exam.
That's right, they're just graded separately.
When you write the final exam, how many questions do you usually take from each of the?
It depends what questions I choose because there's so much difference in the amount of time it takes, but I think most likely it'll be like one question from each of the remaining topics. So that's going to be 2 questions. And then maybe 3 more questions taken randomly from throughout the semester. And they'll be definitely like on the easy side of the practice problems and simple questions so that just so you have enough time in the amount of time.
So they shouldn't be tricky. They're questions that we should be able to do as long as we know the material.
The way to get ready for them is still the practice problems, and they'll be like the practice problems but easier.
Okay.
Yep, and they'll be very straightforward.
Practice problems as opposed to the previous exams.
Yeah, I mean, you could think of the previous exams as like giving you more practice problems, but yeah, they'll be along those lines. You'll recognize similarities with the practice problems and with the exam questions from before, yeah.
Will there be, you said in the final, there's also going to be a quiz on the final?
Yeah, is that right? 1, 2, 3, yes, that's right.
Okay.
So a cumulative quiz on the final, yep.
A cumulative quiz.
Yep. Any other questions about exam 4? Yes. So I guess that would be what I'm calling quiz 3. And so for quiz 3, you need to be comfortable with the circular motion notes. Any other questions?
Were you posted last Wednesday?
Now I have. I just did it today, yeah. And then problem set number 2. So I'll get it up tomorrow, roughly tomorrow. And you'll just turn that in. And that'll just be due by let's say the end of finals week. I mean, in a way, I should say it'll be due a week after it's given, just so that you do it, because it won't take like that much time or anything, but I don't care when you turn it in, as long as you turn it in before the last day of finals.
You can email it to you?
Yeah, if you scan it and email it. Why don't I make a Dropbox on D2L? That seems to work a lot better. Things don't get lost, but yeah, that's fine with me. But you have to get it in by the end of finals week because that's when I have to turn the grades in. So I recommend, now you can do what you want. You're all adults. But I recommend doing it well before then.
If we had it before, will you like give us feedback on it?
If you make an effort, like come talk to me during lab or whatever, I'd be happy to let you know where things are going. I couldn't probably do it with that exact format where you like turn it in and I look it over, but yeah, I'd be happy to look at it with you. And then I guess the last thing is all labs and class are canceled for next Wednesday. For Thanksgiving. All right. Any other questions? I think that's pretty much what's coming up in the next couple weeks. Is it Monday? Yeah, I think that's when it usually is. So, so Monday, the first day of finals week, at the normal class time, normal room. So in here. Yeah, but the test isn't written to take any longer. So yeah, you're welcome to take. I think you have 3 hours to work on it, but I mean it'll be written to be a 1 hour test.
Is there a day class that day that you can take the final if you have to take it?
You can take it with the day class, but it's not that day. It's the last day of finals week. Which actually, I know that a lot of people hate that, but it is sort of nice to like have time to work on stuff after you finish your other things. But so yeah, you can either take it the first day of finals week or the last day of finals week. Any other questions? Okay. So now we're done with uniform circular motion. Okay.
Could you put a discussion group up on D2L in case people want to discuss problems or ask for help?
Yes, I need to write a note to myself.
But Wednesday's
It's on now.
on YouTube.
On YouTube.
On YouTube.
It's up now.
Okay.
It just wasn't earlier today. Okay, discussion group. Yes, I'll do that. So we're done with uniform circular motion, but we haven't done non-uniform circular motion yet. So what defines non-uniform circular motion? That's right, not a constant speed. So the speed is changing. Yep. We know that anything that's moving in a circle needs to have an acceleration causing the direction change, right? There always needs to be an acceleration that's perpendicular to the velocity vector. But now we're going to also have an acceleration that's parallel to the velocity vector. So remember that if you have an acceleration parallel to the velocity in the same direction, then the object's speeding up. If it's parallel to the velocity and in the opposite direction, then it's slowing down. So if the speed is increasing, we're going to have a tangential acceleration in the same direction as the velocity vector. And if the speed is decreasing, we'll have a tangential acceleration in the opposite direction of the velocity vector. So that's what we're going to use to get the direction of the tangential acceleration. The magnitude of the tangential acceleration comes from the definition of acceleration that we used in one-dimensional kinematics. So tangential acceleration magnitude is equal to the speed at the later instant minus the speed at the earlier instant divided by the elapsed time. Before we do an example problem, I want to do just a few kind of intuitive examples. All right, so first, let's say that something's moving in this circular path, going counterclockwise. And let's say that we're analyzing this point in the circular motion. So first, let's say that it's uniform circular motion. What's the direction of the velocity vector, the centripetal acceleration vector, and the tangential acceleration vector? Okay, so just look at that for a second and see if you can draw those arrows. Okay, what's the direction of the velocity vector? So it's going this way. We know that it's tangent to the circle. So the velocity is like that. Any questions about that? What's the direction of the centripetal acceleration? That one's always towards the center, whether it's uniform, non-uniform. So that's AC. And what's the direction of the tangential acceleration? That question doesn't even, there's no tangential acceleration because it's uniform circular motion. So only if it's speeding up or slowing down do you ever have tangential. Okay? So now for part B, say that you have the same circle, still going counterclockwise. And we're interested in this point again. Now say that it's speeding up. What's the velocity, centripetal acceleration, and tangential acceleration directions? And also, now this is going to be very rough, but what's the direction of the total acceleration vector? So see if you can write those down. What's the direction of the velocity vector? It's the same as it was before. Yeah. Every time you guys do it in the direction on there, it's opposite of what. Okay, so there's the velocity vector. Centripetal acceleration vector. Okay, that's insulting your intelligence. How about the tangential acceleration vector? Same as velocity because it's speeding up. And now, anybody have an idea about question? Oh, about the total acceleration vector? Yeah, so the way that works is you're going to add up the centripetal and tangential accelerations to get the total acceleration. So you'll put one of those, the tail of one of those at the head of the other one, like that. And then your total acceleration is going to be something like this. Okay. Now, we can't define that direction for sure unless we knew what the relative magnitudes were of the tangential and centripetal. Like if the centripetal was really small, this would be closer to the direction of the tangential. If the tangential was really small, it would be closer to the direction of the centripetal. But we can break it up into kind of a quadrant type thing. Any questions about that?
How would we actually show the answer for acceleration?
Well, I just want you to recognize that. So this isn't something that'll be on the test. This is just something that can help you with problems because all of these directions you need to come up with from your knowledge of how this stuff works, you know. But if I did ask a question like this, I would just want you to recognize that what you're doing to get the total acceleration is adding up the two parts of you're adding up the tangential and the centripetal to get the total. Any other questions? So now for number 2. Say that this is moving clockwise. And let's say that we're interested in this point. So A, let's assume that it's slowing down. What are the velocity, centripetal acceleration, tangential acceleration, total acceleration direction, and this is the new one. If you added up all the force vectors, what direction would the total force vector be in? So see if you can think through those. I like getting into this stuff because like the more sort of conceptual and like 3D thinking is required, the more people look like they're dancing to Vogue by Madonna when I watch them work on problems, you know? So what direction is the velocity vector? Yep. This way. Centripetal acceleration vector toward the center. Tangential acceleration vector. Yep, good. Total acceleration. Yeah, that's a good way to think about it. It's between these two. So the total acceleration is going to be somewhere in that direction. And now what do we know about the total force vector? So there could be 100 different forces. There could be friction, a normal force, a bird sitting on it, a billion different forces. And we don't know anything about those individual ones, but we do know something about the direction of the sum of all those forces. How do we know the direction of that force? We know it's in the same direction as the acceleration because of Newton's second law. Okay, so this always is in the same direction as the acceleration vector. That's from Newton's second law. So the direction of the net force is this way.
And it's okay to write it that way, even though it's a rough guess of the acceleration vector.
Yeah, right. I mean, if this was right, this would be the direction of the force. The key is just keep in mind that Newton's second law says add up all the forces, they're equal to the mass times the acceleration. That says that the force direction has to be the same as the acceleration direction. Part B. Now let's say that it's speeding up. What are the directions of all of these same things? And it's still going clockwise. So what's the direction of the velocity vector? Yep, that doesn't change. Direction of the centripetal acceleration? Yep. Tangential has to be the same as velocity because it's speeding up. Total acceleration between tangential and centripetal, so somewhere, yep, in this direction. And so the sum of all the forces, same. Yep, that's right. Okay, so let's do one more circular motion problem and then we're done with circular motion. It involves carousel kid. Yeah. Yep, it'll do that. He looks like Charlie Brown, kind of. Okay, so he's going this way. The radius is 2 meters, so he's 2 meters from the center of the carousel. From a top view, it would look like this. Here's his big, ugly melon head. So this distance is 2 meters. His mass is 15 kilograms. And his story arc is as follows. He's sitting at rest, and a bully accelerates him to a speed of, let's say, 8 meters per second. Let's say that happens over a time interval of 2 seconds. And the question is, what's the acceleration vector at the moment when the acceleration magnitude is greatest? Okay, so two types of acceleration go into the total acceleration, right? The centripetal acceleration and the tangential acceleration. The tangential, we're just going to use that equation. It's going to be constant. So that's not going to change, right? So the tangential part of the acceleration there's no maximum or minimum there. That's always just a certain amount. The centripetal acceleration does change, though. Like what makes that change? The radius could, but it stays the same. So what's the other variable that goes into centripetal acceleration? Speed. And the speed's increasing. So the centripetal acceleration is going to be the biggest when he reaches the highest speed, right? So the moment that we're looking for is, like, you can think of it as the instant before he reaches that maximum speed, when he still has that same, so we're going to use that speed of 8 meters per second for the centripetal acceleration to find the maximum total acceleration. Any questions about that? Okay, so the maximum total acceleration magnitude is when the speed is greatest. And that's always the case if you're talking about a constant tangential acceleration, and that's what all these are going to be. Now we can go through the steps of these circular motion problems. This isn't a tetherball problem, so we know that the view we want to take is one where we can see the circular shape. So I'm going to take a top view. And now we have the choice of what point we want to analyze. there are 4 good choices. I guess I'll choose this one. We haven't done one over here yet, so. If the carousel's going this way, what's the direction of the velocity vector? Up. What's the direction of the centripetal acceleration vector? Toward the center. Tangential acceleration. Same as velocity. The magnitude of the centripetal acceleration is v squared over r. The v that we want is 8, because that's when the total acceleration is maximized. So we have 64 meters squared per second squared. Divided by 2 meters. And so we get 32 meters per second squared. So what are the components of the centripetal acceleration vector if we're using a standard coordinate system? That's right. So the centripetal acceleration vector is in the negative x direction. Any questions about that? I know that can get people turned around because you look at this point and you think of it as like it's in the positive x direction from the center. But that vector is in the negative x direction. So this is negative 32, 0. And now the tangential acceleration. First, we have to use that formula. So the magnitude of the tangential is the later velocity, the later speed, minus the earlier speed, divided by the elapsed time. So that's 4 meters per second squared. What are the components of the tangential acceleration? 0, 4. It's pointing in the positive y direction. So this is 0, 4 meters per second squared. And so these two together give us the total acceleration. So what's that? Yep. Add these two vectors together, you get negative 32 meters per second squared, positive 4 meters per second squared. So now we know everything we can know about the right side of Newton's second law. So now draw the free body diagram. When he's in this position, let's see. So shoulders, knees. So that's the view in the position that he's in that we're concerned about. Okay. What forces are acting? So let's go through even the ones that are out of plane. Let's just go through them. So there's the weight, right? That's acting down into the page. So I'll write that here like that. So that's the weight. Then there's a normal force acting up. And then the only other force is the horizontal force provided, applied to him by the carousel. That's the friction. So I'll write that as FF. We don't know the direction of that force. But that's the only force that's in the plane that we're doing this calculation in. So based on those intuitive examples, we know that this friction force has to be in the same direction as this, right? a little down, and a little to the right. Or I should say a lot down, a little to the right. So Newton's second law says the force of friction is equal to the mass, 15 kilograms, times the acceleration, negative 32.4. Can someone multiply 15 times 32? Ooh, I can do that. No. 15 times 32? Really? No. Okay, 480. Oh, yeah. And then 15 times 4 is 60. These are in newtons.
On the test and our works, do you want us to do the weight and the normal?
Like draw those in?
Yeah.
It's fine with me either way. You can leave those out if you want to. Okay, so that's the total force. We calculated, I didn't even ask what I want. I didn't even tell you what I wanted you to solve, I don't think. Oh yeah, what's the acceleration? So we calculated the force. Any questions about that calculation? You know, these problems are pretty kind of recipe type things. I'm not going to, all the questions are going to ask for things very similar to this, give you information very similar to this. So you just have to get used to going through those steps.
The question didn't ask the friction force?
I forgot to ask it, but I meant to.
Oh, okay.
Kilograms, yeah. So what's the acceleration at the moment? And what's the force of friction? That's what I meant to ask. Any other questions about that?
So then the first answer for when the acceleration was created is just
The negative 32.4. That's right. And then how would you get the magnitudes of these if I asked for them? The magnitude of the acceleration, say. You take the square root of the sum of the squares. It's the hypotenuse thing. Because you have a vector here that's something like this, right? And the components give you this and this. So you're calculating the hypotenuse of a triangle. And the same thing for the force. To get the magnitude of the force, you take the square root of 480 squared plus 60 squared. No. I don't think so, unless those calculations are on the practice problems, but I don't think so. But it's just a good thing to know. Good thing to keep reminding yourself. Like if you have the vector components, that's how you calculate the magnitude of the vector. Square root of the sum of the squares.
I have a question.
Yep.
I'm confused about why it's shaped more down than it is left. I thought it's negative 32.
Oh, I drew it wrong. I drew it wrong. That's why. Because it should be this way.
Yeah.
Yeah. Sorry. Thank you for clarifying that. Any other questions? I drew the acceleration vector to give the acceleration vector direction. I drew it like it was mostly down, but I just read those components wrong. Well, that's all for circular motion. So now we're going on to conservation of linear momentum and conservation of energy. So first of all, what does conservation mean? So conservation means that a quantity stays constant. So this ethereal young lady holding this shovel. Planting this tree. Just because of my love for stereotypes, I'm also going to draw like long hair with sort of like a Woodstock style haircut and John Lennon glasses. Oh, and a bandana or something, and a peace symbol. Yeah, it's true. That still works with what I'm trying to do. Okay, this woman, this is not conservation. Or, you know, this is not nature conservancy. Nature conservation. If she puts that tree in, then she's changing the number of trees. Okay? And as another example, people who demand that Obama be impeached are not conservatives. If you were like really a pure conservative, you would just vote for incumbents every single election, every incumbent. So conservation of linear momentum, that's the first one we're going to talk about. And it says that during collisions, it actually says this has to be true for times other than collisions, but conservation of linear momentum we're only going to use for calculations involving collisions of things. During collisions, the total linear momentum of objects is conserved. Where linear momentum and it's always written as a lowercase p. It's a vector quantity. I don't know why they use a p, but m is already taken. I know that much. is equal to the mass of the object times its velocity vector. The SI units of linear momentum is kilograms meters per second. And so here's sort of a mathematical way of writing it. If objects A, B, and so on have no net force acting on them, in the chosen coordinate system, then add up the momentums of all of those objects before a collision. You get the mass times the velocity of A before the collision, plus the mass times the velocity vector of B before the collision, so on. Keep adding them up. This is before the collision. They have to be equal to the sum of all those momentums after the collision. So the mass, or I should have written here, mass of A times velocity of A, mass of B times velocity of B. So those have to be equal to MA VA plus MB VB, so on, after the collision. So notice that for us, for our calculations in this class, that left side of the equation will always represent the instant right before the collision. And the right side will always represent the instant just right after the collision. One thing that's nice about conservation of linear momentum problems is we saw this with problem set 1 that so 1D kinematics isn't, like, of all the things that we've talked about, that's one of the easier things for you now to do, right? But problem set 1, part of the reason it was tricky was because you didn't have any context to tell you what part of the class, what techniques from the class to use on it. You didn't know if you had to calculate forces and use Newton's second law or calculate two-dimensional kinematics, right? And so it took a little while to figure out, oh, like I can just do this as a one-dimensional kinematics problem, right? That's always, in physics classes, math classes, that's always one of the trickiest things. When you all of a sudden go from just applying the techniques that you're doing at that time in class to having this whole set of techniques available to you and having to figure out which topic, you know, to use for a problem that you see develop outside your window or something, you know what I mean? So that's always a tricky thing. And anytime you can get your hands on a way to know what technique to use at what instant, it's helpful. Conservation of linear momentum, you're always going to use for the same thing. If there's a collision in the problem, conservation of linear momentum is what you're always going to use to go from right before the collision to right after the collision. Okay, so that's a nice thing to sort of center yourself on in problems. If there's no collision, then you know you're not using that. If there is a collision, you know you're using it just for the collision itself. Anything that happens before or after the collision, you'll have to use something else for. Okay? So this equation think about collisions. Think about a few different types of collisions, you know. Think about a few different types of objects colliding. And then think this conservation of linear momentum, is that enough information for us to go, usually we'll know the velocities, the momentums of objects before the collision and be trying to calculate the velocities after the collision. If this is true for every type of collision, right? If this is true for Play-Doh running into Play-Doh and it's true for pool balls running into pool balls, does it seem like this should be enough information to know what the velocities are going to be after the collision? Do you see what I'm getting at? Like, if you throw two pieces of Play-Doh together, they hit each other and drop down to the floor as a single lump, right? If you throw two pool balls together, they bounce off of each other, right? They could have been coming in with the exact same masses and exact same velocities, but what they do after the collision is totally different, right? So there has to be something else that we need that's specific to the type of objects and the type of collision, okay? So it sort of makes sense intuitively that this isn't enough information yet. We need to know something about the collision itself. So let's say conservation of linear momentum isn't enough to calculate velocities after the collision. You also need to know something about the type of collision. And we're going to separate this into two very simple opposite cases that are just, again, these are just going to be like approximations of what really happens. We're going to take the two extreme examples, and the two kinds of collisions we're going to deal with are things that bounce apart very strongly. We'll see that it has to do with energy being conserved in some way in that collision. So things that bounce apart and things that stick together. So the things that bounce apart those kind of collisions are called inelastic collisions. Some examples of, no, I'm sorry. Let's actually change this to be, this first one should be the ones that stick together, because that's the first one I'm going to talk about in detail. And those are the inelastic collisions. So some examples here are a person catching a ball is an inelastic collision. Another one would be train cars that latch together when they collide.
So why would the person catching the ball be a tricky one if they're grabbing onto it instead of the ball hits them and sticks to it?
They just have to, the key is just that after the collision, they have to have the same velocity.
So the ball hits them and it drops instead of bouncing back?
After the collision, whatever the person does, the ball does too, you know? So like someone catches the football and keeps running, they have, right after the collision, they have the same velocity. And that's what's required for this. If two Play-Doh balls hit each other, they both fall to the ground. They both have the same velocity vector after the collision. So that's the key. And then the other case is if they bounce apart. Those are called elastic collisions. Mathematically, these are going to be the more difficult ones. It's just messier, really. It's not conceptually more difficult. So examples here are like pool balls colliding. Oh, elastic. It took me a while, like when I first heard the term elastic, to make the connection between like elastic, like Fruit of the Loom waistband elastic and like an elastic and like physics elastic. Because I always thought like elastic that you buy, like, and this is useful to make this connection because it tells you what elastic means anytime you see the word, even in situations where you haven't heard it before. So the elastic that you buy, and you know, I'm sure everybody here makes their own underpants, and I know I do. So what is it about that elastic that makes it elastic? Like what's the thing that makes it elastic? I always thought, well, it stretches. That's what makes it elastic. But it's not the stretching that makes it elastic. It's the fact that, because like lots of things could stretch, Play-Doh again, you know, it comes back. That's what makes it elastic. Any energy you put into it, when you let go of it, that energy comes back. And so that's the thing about objects that bounce. They hit together, they deform and bend, but eventually they spring back into their normal shape, and all that energy sends them flying away. Okay. Okay, so the first case that we're going to deal with is inelastic collisions. This is the one that's defined by objects sticking together. And what that means to us is that after the collision, objects have the same velocity vector.
So when you say,
Mhm.
when you say after their collision that objects have the same velocity vector, you're talking about the two actual objects at the time after collision having the same, not saying that it's the same velocity vector as before.
Right. As each other. So an example is, so if there was a person standing on a skateboard, and a ball is thrown to them, say that before the collision, the ball has a velocity of 15 meters per second. And let's say that the ball has a mass of 0.4 kilograms and the person has a mass of 50 kilograms. Then after this person catches the ball, what's the velocity of the man and the ball together? So one thing to notice is we'll always do conservation of linear momentum problems from a top view. And that's because if you look at this problem, the person here up and down has no net vertical force acting. Gravity's acting, but it's being counteracted by this normal force. But the ball has gravity acting on it and nothing counteracting that. So there is some non-zero vertical component to the force on these objects. And remember that conservation of linear momentum requires having no net force on the object in the coordinate system you're dealing with. So we want to use a top view because horizontally, there aren't any net forces acting on the system. Okay, gravity's acting out of the plane of the coordinate system. The normal force is acting out of the plane. So to us, then the problem looks like this. So the ball's coming in this way. The person's standing here. So before the collision, there are two objects in this system. So first, to calculate the momentum of the ball before the collision, we have the mass of 0.4. What's the ball's velocity vector before the collision? Positive 15, 0. And then we have the mass of the man, 50 kilograms. What's his velocity vector before the collision? 0 if he's just standing there. And after the collision, they both have to have the same velocity vector. So in fact, you could just think of them after the collision as this collision turns them into a single object with a mass of 50.4 kilograms, and we're trying to calculate what its velocity vector is. Okay, so after they have a mass of 50.4, and we're trying to figure out what this velocity vector is. So this, well, he's standing on a skateboard. I mean, he's not moving. He is on a skateboard. Anybody know why I put him on a skateboard to do this problem? Yeah, because if he was standing there, the friction between his shoes and the ground would mean that we can't use conservation of momentum. That would be, you know, forces acting in our coordinate system. Okay, so the first equation here says 6.0 is equal to 50.4 Vx. The second equation says 0 is equal to 50.4 Vy. And so the velocity vector after the collision is equal to 0.119 meters per second, 0. Does that make intuitive sense that they're moving so slowly after the collision when the ball came in at 30 miles an hour or something? Question? Nope, no difference. Except you have to wait until that motion is done. The collision takes, so if it takes them half a second to go from here to against their body or whatever, then your instant after the collision can't be until they're done with that motion. So the reason that their velocity is so low compared to the ball's starting velocity is because the man is so much heavier, so much more massive than the ball. Essentially what you have is the velocity of them after the collision is much closer to the velocity before the collision of the more massive thing, of the much more massive thing. And, you know, you could think of, it would be an inelastic collision if a semi-truck and a smart car hit head on and stuck together, you know. And you know from bad stories about it or whatever, that after that collision, their velocity is going to be much closer to the starting velocity of the truck than it is the smart car, you know. And that's the same effect. You could do that same calculation that way. Any questions about that? Okay.